Should I start sharing my screen?
Yeah.
Yeah, you can.
Okay.
So Atul, I think it's live. You can introduce
Okay.
it.
Sure. Good afternoon, everyone, and good afternoon to Siddhi. So it's good morning to Siddhi. Sorry. So it's our pleasure to invite her to give a talk in the seminar. So I know Siddhi from 2017 when I visited Queen's. So Siddhi got her PhD from Queen's University under the supervision of Professor Ram Murthy, and currently she is a postdoc at Penn State with Winnie Lee. So she'll be talking on special values of L functions. Over to you, Siddhi.
Thank you. Thank you so much, Atul. And thank you, Gaurav, also for inviting me to speak over here. It's my pleasure to speak in the seminar. Um, so, in order to keep the talk accessible to students, I will mainly be giving an overview of the topic of special values of L functions. And only towards the end, I will discuss some recent work. Um, Anyone who has questions, please feel free to interrupt me and I will be happy to answer. Okay, so to begin with, I would like to start with a question that is of general appeal, which is this conjecture of Erdős. All right, so this conjecture of Erdős concerns summation of some coefficients over n. Uh, we know that typically the harmonic series summation 1 over n is divergent. But if we replace the ones by plus ones and minus ones periodically, then the series converges to log 2. We know that log 2 is not 0, but not only that, we know that log 2 is transcendental. Let me recall that transcendental means that it does not satisfy any polynomial with rational coefficients. So we see that just by changing 1 to the periodic plus minus 1 sequence, we get a very interesting number. Then one may ask, why just have period 2? What if you have a random plus minus 1 sequence? Can we say something about that? If you have a random plus minus 1 sequence, then if the series converges, it will converge conditionally. And so the Riemann rearrangement theorem will tell you that you can rearrange it to any number you want. Structure to that sequence. One structure that we observe in the plus minus 1 in the log 2 series is that the plus minus 1 sequence is periodic with period 2. Instead, let's say if you take a plus minus 1 sequence which is periodic with period any integer capital N, then would you get a non-zero number, and in particular would you get a transcendental number? One instance of such a conjecture, such a phenomena is this conjecture that was put forward by Erdős in 1964. So Erdős said that if we have a periodic sequence of plus minus ones, where you have 0 at the period, at the multiples of the period, so here capital N is my period. So whenever I have multiples of the period, I introduce a 0, and for all other coefficients inside, I introduce a plus 1 or a minus 1 randomly. Then if you look at the corresponding infinite series, summation f of n over n, this series converges to a non-zero number. The fact that this series, if it converges to non-zero, is transcendental will follow from Baker's theory, as we will see later on. But it is important here that this number is a non-zero number. Okay, so this is a very curious conjecture. It is very easy to state, and so I think it has a general appeal. What one can immediately observe is that this infinite series will converge if and only if the mean value of the function over the period is 0. You can see this using partial summation or any other technique that you like. But this mean value being 0 in our case would mean that the period is odd and there are equal number of plus ones and minus ones. All right. So what do we know about this conjecture in the case? So we know that n is odd. There are many intermediary results, but one of the important results in this context is the result of Murthy and Sharda, where they show that when n is 3 mod 4, this conjecture is true. And the other case, namely n congruent to 1 mod 4, is still open. And this is, I think, one of the main themes that make this question very interesting, that such a easy to state conjecture or easy to state problem is still open in a particular case. Now, I would like to point out a certain important structure to this Erdős conjecture. Namely, Erdős is introducing the zero at the periods. If we take out that zero, and if we take a periodic function which has plus minus ones throughout for all residue classes, then there is a counter example. Namely, there is a function modulo 36 which was found by Tengli, such that this infinite series does equal 0. So it is important that you have the 0 at the end. There are also heuristics that if you allow zeros in between the plus minus ones, even then you can find functions f such that this series is 0. So it is very important in the Erdős conjecture to have this particular structure to the function. In the passing, I would also like to mention that we do know that the conjecture is true with probability 1. This was proved in the part of my PhD thesis. So we do expect the conjecture to be true 100% of the times, but still the n congruent to 1 mod 4 case is open, and we expect that we would need some new techniques in order to handle this case. Okay.
Sorry, I had a question. This is a good question.
Yeah, please.
So you said it's open for n1 mod 4, but is it actually known explicitly for maybe infinite many values of 1 mod 4, or at least one value of 1 mod 4?
Yeah, so if we have a product of two, so we know it for primes. So any prime congruent to 1 mod 4, we do know. We do also know it when the number has 2 prime factors.
Okay, great.
And some other cases, but basically the general case of 1 mod 4 is open.
Right. And when you say it's true with probability 1, does that mean there's almost, I mean, it's true for all but finitely many n, or which are 1 mod 4? No.
Yeah, that's a good question. So by probability, yeah. So by probability 1, I mean probability 1 of Erdős functions. So for example, let's say we look at all Erdős functions with modulus up to x, and out of them we look at the proportion of the Erdős functions for which this series equals 0. Then that proportion goes to 0 as x goes to infinity.
Okay, great.
Yeah. So that in that sense, we mean it for probability 1 of Erdős functions, not probability in the n congruent to 1 mod 4 case. Okay, so what does this have to do with special values of L functions? To answer that, let me first talk about what an L function is and what do we mean by that. So although the term of L function was probably coined by Dirichlet, the idea of an L function is nascent in the work of Euler. And we can see that even in as back as 1730s, Euler really had an idea of what an L function might be. So this comes up in Euler's proof of infinitude of primes, where he looked at the identity given by this over here. So here we are just expanding the left hand side and using the fact that you have unique factorization of natural numbers into primes, and then we get this particular identity. This will hold analytically for any real number x bigger than 1. So if there are finitely many primes, the left hand side will be true, will be finite for all values of x, whereas the right hand side we know diverges as x goes to 1, and so taking the limit of this identity as x goes to 1, we would get a contradiction if there are finitely many primes. This was Euler's proof of infinitude of primes, and this here we see is nascent the idea of an L function. This motivated Riemann in 1859 to define the right hand side here as a function of a complex variable instead of a real variable, and that is what we call the Riemann zeta function today. So the Riemann zeta function is given by this series, the infinite series, which is absolutely convergent for real part of s bigger than 1. It has analytic continuation, which was proved by Riemann, except for a simple pole at s is equal to 1. Moreover, there is a certain symmetry between the values of the Riemann zeta function, namely it satisfies a nice functional equation relating the values at s to the values at 1 minus s. Here C is the completed zeta function where we introduce certain gamma factors as well. This also was proved by Riemann. And we later on now know that the prime number theorem, which counts the number of primes up to a real number x, that is equivalent to the non-vanishing of the Riemann zeta function on the vertical line real part of s equal to 1. The famous Riemann hypothesis states that if you have any zero of the Riemann zeta function in the critical strip, namely the strip between real part of s equal to 0 to the real part of s equal to 1, then it must have real part equal to half. It must lie on the half line. Of course, we know that the Riemann hypothesis is still open. However, this whole structure gives rise to other interesting contexts when we expect such a structure, and those contexts we will call them as L functions. So the idea that an L function can be used to study primes was of course introduced by Riemann, but it was exploited by Dirichlet, and he used that to prove infinitude of primes in arithmetic progressions. So Legendre had conjectured that not only are there infinitely many primes, but if you look at a particular residue class, a reduced residue class modulo a number, then there are infinitely many primes in that residue class as well. What Dirichlet thought in 1840s is if we can emulate Euler's idea and prove the same conjecture of Legendre by using this infinite product. So if one expands this infinite product, because we are looking at a particular residue class, one can think of expanding that in terms of products of the series of this form, which looks very similar to the series that Euler had considered. Here chi is a Dirichlet character, but if you don't know what it is, then one can just think of it as a periodic sequence that is multiplicative. That means if you take any chi of m and chi of n, then the product of chi of m times chi of n is just chi of m times n. Moreover, this will be supported only on co-prime residue classes mod capital N. So this sequence has a lot of structure in it, and it captures in particular captures all the arithmetic progressions modulo n. There is one special character, one special chi among all the Dirichlet characters mod n, which is the principal character. This principal character just picks out the co-prime residue classes mod n. And because it is 1 on co-prime residue classes, 0 otherwise, it behaves essentially like the Riemann zeta function. In particular, it will have a pole, a singularity at x is equal to 1. So this series over here will diverge at x is equal to 1 if you're taking the principal character, whereas if you take any non-principal character, then the series will converge all the way up to 0. Okay, so Dirichlet established this identity, and using this identity, one can then see how we would emulate Euler to prove infinitude of primes in A mod n class. That is by taking the limit as x goes to 1 on both sides. Now, on the left-hand side, if there are only finitely many primes congruent to A mod n, the left-hand side product will be finite for all values of x. On the right-hand side, we have this principal character, which has a singularity at x is equal to 1. As long as that singularity is not cancelled by a 0 of another series corresponding to chi mod n, then we are in business. Then we do the same thing as we did earlier for Euler here. Take the limit as x goes to 1, the right hand side would go to infinity, the left hand side would be finite, and we would get a contradiction. So as long as all the series, all these chi of n over n are not 0 for non-principal characters, we get infinitude of primes in arithmetic progressions. So this gives an arithmetic significance of the value L1 chi. So here is the L from the L functions that we are going to look at. In general, we are going to have L functions that have such a series representation. This kind of a series representation is called a Dirichlet series, where instead of chi of n, you might have other coefficients, a of n, and we look at this function as a function of a complex variable instead of a real variable, which was Euler and Dirichlet's idea. So these kind of functions then satisfy analytic continuation, functional equations in nice cases, and we would like to study their zero distribution in number theory. These are the general L functions that we would be looking at. Okay, now let's come back to the problem at hand, which we were looking at L1 chi. So in order to prove the infinitude of primes in A mod n, we would like to show that L1 chi is not equal to 0. Okay, how does one go about showing that? Typically, the proofs of non-vanishing of this value are split into two cases. One case of the character being complex, that is the character taking values in complex roots of unity, and the other one is when the character is real, namely the chi of n, the coefficients are plus minus 1s and 0. The simplicity that comes when you consider complex characters is because there are a pair of them. If you have a complex character chi, you also have another character chi bar. Because you have chi and chi bar, if L1 chi is 0, then L1 chi bar is 0. We can kind of put them together into this product and look at this entire product. Now there is the principal character which has a singularity at 1, but that singularity will be cancelled by one of the zeros, and you will introduce another 0 because you have two characters that have the value 0. So this entire product will have a 0 at s is equal to 1, and from there one can deduce a contradiction. So the case of complex characters is relatively easy. In the case of real characters, in order to show non-vanishing, it is more trickier. There are many different ways of doing it, but two of them would be an analytic approach and the other one would be an arithmetic approach. An analytic approach is when you consider the series LS chi together with the Riemann zeta function. If you do that, you will get another Dirichlet series with positive coefficients, and then one can apply Landau's theorem, which is a theorem in analytic number theory, and then conclude that L1 chi is not 0. The arithmetic approach, which was taken up by Dirichlet, was to connect the value L1 chi to the class number of the corresponding quadratic field. We will see this class number formula in a second. But because this class number formula relates the value L1 chi to something non-zero, something arithmetic, which we know is non-zero, we get that L1 chi is non-zero, and hence there are infinitely many primes in our reduced residue class. The important point to note here is that all these proofs, whether it be of the complex characters or the real characters, rely heavily on the fact that chi is multiplicative. It has this nice structure of chi of m times chi of n is equal to chi of m times n. However, we will see later on that we would like to approach this non-vanishing problem where our coefficients need not be multiplicative, and that is the main issue. Okay, are there any questions so far? Okay, so now let me just give you a couple of examples of other L functions to keep in mind as we move along. There are L functions associated to number fields where we look at how many ideals are there of a particular norm and then construct this series like Dirichlet. These functions are called the Dedekind zeta functions, and they enjoy similar properties like the Riemann zeta function, but they are of a higher degree. Similarly, if you have a modular form, we know that it has a nice Fourier series expansion. If we take the Fourier coefficients of the modular form as the coefficients and construct this Dirichlet series. That series is also a nice series. It has analytic continuation and functional equations, so on and so forth. These are also nice L functions to keep in mind. There are other L functions that are associated to representations of Galois groups called Artin L functions, but we won't go into that. These are some nice examples to keep in mind just as we move along. So although these L functions are functions where you insist on Euler product, means that the coefficients that you're looking at are multiplicative, and functional equation, the relation between values at s and values at 1 minus s. As we go along, we will see that our L functions need not always have an Euler product or functional equation. Instead, we will mostly be focusing on Dirichlet series representations that have an analytic continuation except for a possible pole at s is equal to 1. So as long as we have that structure, we will call it an L function. That might not be standard, but that's what we will stick to for today's talk. Okay, so these are the objects that we want to look at, these kind of L functions. What are the questions that we want to ask about these L functions? The questions that we want to ask are about their values at positive integers. So what is the value at 1, what is the value at 2, and so on and so forth. What type of questions would we ask? So the type of question that is motivated from our previous discussion, namely L1 chi being not 0, is whether the value of a particular L function at any positive integer is 0 or not. If our L function has an Euler product, namely if our L function has multiplicative coefficients, then it is easier to answer this question, like in the case of the Dedekind zeta function or the Riemann zeta function. We know none of the values to the right of 1 are 0. However, if you don't have an Euler product, then answering this question can be quite tricky. There are other examples where this question might have some more arithmetic significance. For example, the Birch-Swinnerton-Dyer conjecture, where you're looking at the L functions associated to elliptic curves, and the order of vanishing at the central point is going to tell us rank of the elliptic curve, the group of the elliptic curve. So this kind of a question may have a lot of arithmetic significance as well. And so this is one of the type of problems we will address today. The other type of problem would be whether the value is rational or irrational, algebraic or transcendental, more coming from the following theorem of Euler. So in his exploits in the 1740s, Euler proved that the value of the Riemann zeta function, which we saw earlier, at even positive integers can be evaluated explicitly in terms of a rational number, which is this Bernoulli number, and powers of pi. Because we know that pi is transcendental, thanks to Lindemann, and that the Bernoulli number is a rational number, we see that the values zeta of 2k are all transcendental. They are transcendental and algebraically dependent because all of them have the same ingredient of transcendence, namely pi. Right. So because we know that such a theorem is true for the Riemann zeta function, one may ask if similar algebraic transcendental natures are known for other values of the zeta function or other values of L functions in general. For the Riemann zeta function, there is a strict dichotomy in the nature of values. We do know how zeta 2k behaves, but we do not understand how zeta 2k plus 1 behave, the odd zeta values. They are all conjectured to be transcendental, but none of them are proven to be so. The best that we know is a theorem of Apéry in 1978, where he showed that zeta 3 is irrational. But we still do not understand if any of the values are transcendental or not. Okay, so this is one of the type of problems. One may ask, when can one expect a nice answer to the question of algebraic transcendence? When should it be easier, like it was in the case of Euler, and when should it be hard, like it was in the case of all zeta values? Although we do not know a definitive answer to that question, there is a philosophy of which was put forward by Deligne, that such considerations depend heavily on the functional equation satisfied by the L function. So suppose you have an L function that satisfies a functional equation of this type. Here, gamma s denote the gamma factors that come along with the L function. We call a number m critical if it is not a pole of any of the gamma factors. For example, in the Riemann zeta function case, if you look at the functional equation, then the even positive integers are critical, the odd positive integers are not. And the philosophy of Deligne states that if you have a critical value, then that critical value can be split up into two parts. One part is the algebraic part, and the other part is a period which we expect to be transcendental. So the period part is going to give us ingredient of transcendence. So this is what is happening in the case of Euler here. We have the algebraic part coming from the Bernoulli numbers and the period part, which is the pi, the 2 pi I. Okay, so this philosophy is general. We do not know this philosophy for many L functions, but we do expect that the theorems like Euler should hold for many nice L functions, and that is known in several cases, and it is an open area of research. Okay, so these are the two kinds of questions. Other kinds of questions that one may ask about the values are there any relations among the values? Like, we might know that the values are individually either algebraic or transcendental, but like for the even zeta values, all of them had the same ingredient of transcendence, namely pi. Should we expect something like that for odd zeta values? And the conjecture says no. There is a folklore conjecture which predicts that pi, zeta 3, zeta 5, zeta 7, all of them are algebraically independent. These kind of questions also are interesting and are a good area of research. Looking at algebraic independence is often hard because algebraic independence relies on showing that there is no polynomial relation. However, looking at linear independence is more kind of doable, more approachable. Okay, and there are some recent results of Ball, Revol, Zudilin about looking at the linear relations among the odd zeta values and showing that infinitely many of odd zeta values are irrational, so on and so forth. Okay, this is another kind of question. And the last kind of question that I would like to point out is whether these values have an arithmetic or geometric meaning. This is like the class number formula that I alluded to earlier. This is the Dirichlet class number formula where he is associating the value at 1 of the L function of a quadratic Dirichlet character to the arithmetic quantity of class number of that corresponding quadratic field. So these are the kind of questions that are generally asked. In our today's talk, we will be focusing on looking at linear relations among values of Dirichlet L functions in particular. Okay. So what do we know about values of Dirichlet L functions? Let me recall that we are going to be looking at L functions associated to characters of Z mod n Z star, extended to the entire group, the entire ring of integers periodically. And because you are extending from Z mod n Z star, we will have a multiplicative sequence, chi of m times chi of n is chi of m times n, that is supported on co-prime residue classes mod capital N. This it is important that we have a multiplicative sequence that is supported on co-prime residue classes. So for this sequence, as I said before, we attach an L function, a Dirichlet series, chi of n over n to the s, and we want to understand values of this particular L function. So one may immediately ask, is there an analog of Euler's theorem for these Dirichlet L functions? And the answer is yes. However, it took actually 200 years after Euler in order to understand that there is an equivalent of Euler's theorem in this situation. This was proved by Hecker, where he showed that the value Lk chi is an algebraic multiple of pi to the k whenever the parity of chi and the parity of k are the same. Namely, both k and chi are odd, or both k and chi are even. Then one can say that Lk chi is pi to the k times an algebraic number. Again, this is an example of critical values. When k and chi do not have the same parity, then they are non-critical values, and understanding their nature is probably as hard as understanding the nature of odd zeta values. Except for the case when k is equal to 1. When k is equal to 1, we have made remarkable progress thanks to the theorem of...
Yeah, so in Hecke's theorem, k is positive, right?
Yes, yes.
Okay. We are not talking about negative integers.
No. In this entire talk, I'm not going to be looking at negative integers at all.
Okay.
Yeah, neither 0. I will only start from 1, 2, and so on and so forth.
Okay, thank you.
Yeah, so although we don't understand Lk chi when k and chi have opposite parity in general, the only case of understanding a non-critical value is the case when k is equal to 1. When k is equal to 1, L1 chi for chi even is known to be transcendental, and we will see that that is known because L1 chi can be expressed in terms of a linear form in logarithm of algebraic numbers, and that can be understood using Baker's theory of linear forms in logarithms. So thanks to that theory, we can understand that L1 chi is transcendental. But after understanding algebraic or transcendental nature, as I said, the next step is to understand relations among these values. And so the question that we will focus on is, are there any linear relations among values of the Dirichlet functions? Okay, so if you want to understand linear relations, let's say you have k to be bigger than 1, then summation c chi Lk chi can be rearranged to look like a Dirichlet series evaluated at k, whose coefficients now are summation c chi chi of n. Because you are summing a multiplicative sequence, the multiplicative structure now may be lost, and so we have a periodic sequence that need not be multiplicative. So this tells us that in order to understand relations among these values, we have to enlarge our scope of ideas and not only look at values of Dirichlet functions, but values of Dirichlet series where the coefficients are periodic, not necessarily multiplicative. So that is what we do. Let's take a general setup. This general setup, you are taking any function that is a periodic, let's say period with capital N, and associated to this periodic function, you can have an L series or a Dirichlet series, summation f of n over n to ds. This will be absolutely convergent for real part of s bigger than 1, but we can rearrange it and see that it is actually a linear combination of these functions. These functions are actually essentially the Hurwitz zeta functions, which are the shifts of the Riemann zeta functions, which we understand very well. And because they satisfy an analytic continuation to the entire complex plane, except for a simple pole at s is equal to 1, the L series associated to periodic functions also will have an analytic continuation with a pole at s is equal to 1, and the corresponding residue will be the mean value of the function. Hence, whenever we want to study the value at 1, we will have to ensure that the mean value of the function is 0, and this will be assumed whenever I talk about the value at 1. I will be assuming that the corresponding function has mean value 0. Okay, so these are the objects that we want to look at, L series associated to periodic functions, and we want to understand the values of these L functions at positive integers. What kind of information are we looking for? We are looking for whether these values are 0 or not, and can we say anything about their transcendental nature. Okay, because of the pole at k is equal to 1, we will see that there is a rigid dichotomy. The situation at k is equal to 1 is drastically different from the situation for k bigger than 1. Because we know Baker's theory of linear forms and logarithms, the transcendental input for k is equal to 1 is known, whereas we will see that for k bigger than 1, the functions involved are not as well understood, and so the transcendence input is not known. However, sometimes the situation for k bigger than 1 is easier because there is no pole to keep a track of. So there is some nice interplay over there. Okay, so for these values, what ingredients do we need? So behind the scenes are special functions, and actually asking for understanding values of these L series is in disguise asking for relations among special values of certain special functions. So the two special functions that immediately seem to crop up to our mind are the di-gamma function. The di-gamma function is the logarithmic derivative of the gamma function, and its derivatives, namely the polygamma functions. So the value at 1 is just a linear combination of the values of the di-gamma function, and the value at k is a linear combination of values of the polygamma function. So asking whether this is 0 or not is asking for relations among values of the di-gamma function, and similarly for the polygamma functions. So the Erdős conjecture in particular was asking whether there are plus minus 1 relations among the di-gamma values, and Erdős's conjecture predicts that there are no plus minus 1 relations among the di-gamma values, which is kind of curious. Okay, another ingredient that we can put into this theory is the theory of discrete Fourier transform. Because we have a function on Z mod n Z, a function periodic with period n, you can have the discrete Fourier transform on this group, and associated to that, we have the inversion identity. Using that, one can write the value of at 1 or at k as a linear combination of log of these cyclotomic numbers, or in the case of k bigger than 1, we have values of the polylog functions. And this is why the study at k is equal to 1 is easier, because we understand how log function behaves much better than we understand how the polylogarithm function behaves. Okay, so in all of the theorems that I would state henceforth, the ingredient of transcendence would be at k is equal to 1, understanding how these values behave, which is the Baker's theory of linear forms and logarithms. And for polylogarithms, the analog of that theory is conjectural. So the theorems for k bigger than 1 are conjectural, are conditional, and the theorems for k equal to 1 would be unconditional.
Siddhi, how do you define the polylogarithm function? So it should depend on m, right?
Oh, sorry. I forgot to write an n to the m here.
Okay.
So the mth polylogarithm function is the summation of z to the n over n to the m. So you have, it's like the Riemann zeta function, but with an exponential twist.
Okay, thanks.
Mm-hmm. Any other questions? Okay. So what do we know about the value of these functions? So first, let's look at k is equal to 1. When k is equal to 1, the study of these values was initiated by Chava in the 1960s, where he first posed the question of non-vanishing of these values for prime periods. He was able to solve this when the function is odd, namely when f of n minus n is minus f of n. That is what I mean by an odd function. So if the function is odd and the period is prime, then indeed the value at 1 is not 0. This was proved by Chava. So here he is looking at the functions that are rational valued. Okay, but the general case when do we expect non-vanishing was not known to him. It was later proved by Baker, Birch, and Wersing, where they used Baker's theory of linear forms and logarithms and showed that if you have a function that is supported on co-prime residue classes modulo n, the period. So this kind of a condition should be thought of as kind of primitivity of the support. That is, the function should be supported on co-prime residue classes like the Dirichlet characters. And the values of the function should be disjoint from the nth cyclotomic field. The fact that they should be disjoint from the nth cyclotomic field comes from the fact that we are using the Fourier transform, the n-level Fourier transform, and we do not want the function values to interact very much with the Fourier transform, the character values that we are looking at. And so this can be thought of as primitivity of values in some sense. So if we have these two conditions, namely primitivity of the support and primitivity of the values, then one can indeed claim for sure that L1F will not be 0. One of the immediate consequences of the Baker-Birch-Wersing theorem is that if you look at the case when the period and phi of n, so n and phi of n are relatively prime, then the character values L1 chi will be Q linearly independent. There won't be any Q linear relations among these values. The condition capital N and phi of n are relatively prime is essential to ensure condition number 2, because the characters take values in the phi nth cyclotomic field. And when n and phi of n are not relatively prime, the corresponding question, the corresponding statement of this corollary is open. We do not understand if we should expect any relations or not. Okay. Another remark that I would like to make is that in the Baker-Birch-Wersing theorem, if we relax either of the conditions, that is, if we relax condition number 1 and allow the function to be supported on all residue classes, then you do have functions for which L1F is 0. Similarly, if I allow condition 2 to be relaxed, that is, if I allow non-trivial intersection between the function values and the cyclotomic field, then again there are a whole bunch of functions for which we do get L1F is equal to 0. These functions actually come from linear relations among odd characters. Hence, it is very important to understand how much can you relax these conditions? How much can the condition 1 and condition 2 be relaxed in order to ensure non-vanishing of the value at 1? We also observe here that the Erdish conjecture is a conjecture in the setting where 1 is relaxed. Because the Erdish conjecture is about functions that take plus minus 1 on all residue classes, so the second condition is satisfied in that case, but the first condition is not. When, let's say, when n is not a prime, the first condition would not be satisfied, and hence understanding how much we can relax this condition over here becomes important. And that is what we will be focusing on right now. How much can one relax the support, the support condition? So can we allow rational valued functions taking non-zero values at all residue classes so that we get L1F not equal to 0? This question was first asked by Okada in 1980s, and he obtained a linear algebraic criterion in order to understand this vanishing. So he proved the following theorem, where he said that if you have a rational valued periodic function, then the value at 1 is 0, exists and equals 0, if and only if one looks at the vector f of 1, f of 2 through f of n, then that vector should be a solution of this system of linear equations, where you have phi of n many linear equations of the first kind for every coprime residue class, and omega of n many linear equations of the second kind. Here omega of n is the number of distinct prime divisors of capital N. So we have two kinds of equations. Total we have phi of n plus omega of n many linear equations, and as long as f of 1 through f of n satisfy this system of linear equations, then your value at 1 will equal 0. Here the numbers AANs and epsilon AP, these coefficients are rational numbers. These rational numbers depend only on the arithmetic of capital N and nothing else. So for given any capital N, we can have this system of phi of n plus omega of n many equations. As long as the function values satisfy this equation, we would get that the value at 1 is 0. As you can see that the definition of these rational numbers is quite messy. I haven't actually even defined all the terms in the number AAN because I don't have enough space. So because of the messy definitions of these numbers, Okada's criterion was for a long time ignored mostly as not being very applicable, because although it's an if and only if criterion, although it's a necessary and sufficient condition, one can only use Okada's criterion to show that the Erdős conjecture holds for capital N that satisfy this condition, namely that more than half of the residue classes are co-prime, and that is only satisfied when capital N has 2 prime factors. So the applicability of Okada's criterion seemed to be very restrictive because of
Hang on,
these.
something wrong with your voice.
Oh,
Can others hear?
Yes, I can hear clearly.
Yeah. I am able to hear.
Okay, then carry on. It must be my problem.
okay, thank you. So yeah, as I was saying that the criterion of Okada was regarded as quite messy and not very applicable. However, in recent work, jointly with Ramurthy, we approached the criterion of Okada in a different way. Instead of looking at individual functions such that L1F equals 0, we looked at the entire vector space of rational valued functions for which the value at 1 is 0. Because of Okada's criterion, we know that the dimension of the space would be n minus pn minus omega of n. And then we tried to understand the structure of this vector space rather than individual functions themselves. While doing so, we obtained an explicit basis for this vector space. This vector space we called the Ocada space after Okada. So we obtained an explicit basis for the space, which is very tractable. It's a very usable basis because it's such a easy to use basis. We used it to extend the Baker-Birch-Wersing theorem. So the Baker-Birch-Wersing theorem turns out is not the best possible. One can let the functions be supported on not only the co-prime residue classes but also the prime residue classes. So we extended the support from just co-prime residue classes to also the prime residue classes of the function. Then we know L1F is not equal to 0. And because of this, we also improved all the previous known results on linear independence of the digamma values, because the value at 1 is connected to the digamma values. Also, because we have this basis for the space, now showing non-vanishing for any function becomes easy in the sense that we have an approach for it. To show that L1F is not 0 for a particular f, all we need to do is show that f is not in the basis, not in the span of the basis that we consider. The basis that we have is very arithmetical in nature, and so if one is able to show that that the function values of f are not in the span of the basis, then we have an approach to show L1F is not 0, and this seems very promising in the n congruent to 1 mod 4 case. This is work under progress. One very surprising thing that came out of our study was that the understanding of this Okada space and the corresponding other subspaces of the Okada space is very intricately related to the question of the nature of Euler's constant gamma. Here, gamma is the constant that appears in the Laurent series expansion of the Riemann zeta function around s is equal to 1. We know that zeta of s looks like 1 over s minus 1 plus gamma. This is the constant term, and then higher order terms. This gamma is the Euler-Mascheroni constant, sometimes it is called that way. We do not know whether gamma is irrational even. We expect it to be transcendental. And it turns out that a lot of the structure of this O of n depends on whether gamma is a Baker period. Namely, can you write gamma in terms of log of algebraic numbers? It is expected to be not. And so we expect that gamma should be a completely different object other than the Okada space. But again, this would rely on understanding the nature of gamma. And I think I don't have any more time left. Is that right?
You have 8 minutes.
Oh, I can go for 8 minutes. Okay, thank you. So this was for k equals 1. And I would quickly mention also what we have for k bigger than 1. For values at k bigger than 1, again, we would like to understand non-vanishing and transcendence. Understanding transcendence is difficult because we don't know the transcendence of values of the polylogarithm function at roots of unity. However, there is an analog of the Baker-Birch-Wersing theorem, which was conjectured by Milner, motivated by Chava. So this we call the Chava Milner conjecture. The Chava Milner conjecture predicts that if you have a rational valued function that is supported on co-prime residue classes, then the value at k at any positive integer k should be non-zero. So one can think of this as an analog of the Baker-Birch-Wersing theorem. We studied this conjecture in recent work with Abhishek Bharadwaj, and we found a previously unknown structure to this conjecture, namely that if the conjecture holds for any number capital N, then it also holds for all divisors of capital N. And this was an interesting observation. Moreover, one can do a similar analysis like the Okada space that we did for k equals 1 for k bigger than 1. One can prove an analog of Okada's theorem. That's what we did. And we further analyzed Okada's work and simplified it to a big extent and gave it a different interpretation. So once again, we can consider the Okada space at k, where we put together all functions for which the value at k is 0. What we showed is that for any function f such that LKF is 0, that function should be essentially imprimitive. That is, the function should be such that its L series splits up into linear combinations of these Euler factors times L series coming from functions that are periodic with a lower period. And you are kind of forcing the value at k to be 0 by introducing this Euler factor. So in this sense, LKF is 0 if and only if the function is inherently imprimitive. It is inherently coming from these functions of lower level. And so we discuss a lot of whether the primitive versus imprimitivity of functions, and the imprimitivity is what causes the value at a particular integer to be 0, whereas for primitive functions we do not expect the value at k to be 0 for any k. And I think I'll just stop there. Thank you.
Very nice talk, Siddhi. So very clearly explained. So are there any questions?
Yeah, so for k greater than 1, do you know the precise value of L, k, comma, f?
Yeah, so it is in terms, I mean, we know it in terms of the polylog functions over here. So either you, I mean, if you, sorry, yes.
Yeah, okay.
Yeah, so either we know, I mean, know it in the sense that we know it as a linear combination of the polylog functions or of the polygamma functions.
Okay. So by observing this, you can deduce whether they are transcendental or algebraic.
Yeah, like, so if we understand how values of these functions behave,
Exactly.
then we have hope of understanding the values at K.
Okay. And also, why are you not looking for, again, I'll ask the same thing, why are you not looking for the negative integers? And because the Riemann zeta value is, the critical points are negative odd integers also, right?
Yes, so the reason I'm not looking at negative integers is because my focus comes from understanding the algebraic and transcendental nature. The values at negative integers would be linear combinations of values of Bernoulli polynomials.
Yeah, just rational. Yeah, correct.
Yeah, so they will be rational. So,
So, but in this
not,
case, can you prove that for the negative integers, they are rational?
yes, because if, yeah, so over here you can see that the value, the L series is essentially a linear combination of the Hurwitz zeta functions,
Okay.
these ones, and the Hurwitz zeta values at negative integers are Bernoulli polynomials.
Okay.
So these values at negative integers are again linear combinations, and then as long as f is let's say k valued, where k is a number field, L minus nf would be k valued.
And in all these L function, period is playing role, right? So we cannot handle L function; those are not periodic. Suppose Langland's L function and so on.
Yeah, that becomes more tricky. I mean, there we don't have a classical approach like this where you can just write down these special functions like this. There, the ingredient functions would probably be more complicated, and so I think that is one of the reasons why we don't understand them as well.
Okay. Thank you.
So, Siddhi, I was curious to know if these modular transformations involving the zeta function, or in more general with the periodic zeta functions like these, like Ramanujan's formula for zeta 2 plus 1, there are analogs of that for LKF, for F periodic. Would those be helpful towards getting, because on one side you have this Bernoulli polynomials, of course, you know from their rational function. And then, I mean, the main difficulty, I guess, would be the Eisenstein series part.
Yeah.
So is there any, I know Erdash had worked on transcendence of Lambert series, some simple ones, like 1 upon q to the n minus 1, 1 upon q to the n minus 1, summation of that. I think Florin Luca worked further on such Lambert series, but with more general, I don't have any idea. So have you looked in that?
No, actually, I haven't studied Lambert series much. I haven't given them much attention as much as this. There is some work of Grosswald which comes close, uh, but not in this flavor. And I mean, they, of course, so over there it is important that you have multiplicativity so that you can look at the logarithmic derivative, which has a nice Dirichlet series expansion, and then you can use contour integration and understand that. But here you don't, I mean, you don't necessarily have multiplicativity. So looking at the logarithmic derivative is tricky.
Right. But still, in this setting, there are transformations of that kind, of Grosswald, of Ramanujan. David
Oh, yes.
Bradley has some papers on it.
Oh, I see.
Yeah, so David Bradley, Katayama, and Bruce Berndt also has some papers based on that. So you may want to.
Oh, I see. Yeah, I'll have a look at them. Thank you for
Sure.
letting me.
Yeah. Okay. Nice talk. Yeah.
Thank you.
Any other questions?
Yeah, I had one. Hi, Siddhi. It's a great talk. Very clearly explained. I had a question on this very page that you were showing. Like you said, conjecturally, you had proved some results for the k greater than 1 case, right? So, what was the conjecture? I missed it. No, this.
Oh,
Okay.
sorry. Here?
No. Okay. No, not this. The previous
Oh,
page that you were on, like F, L, whatever. Sorry, combination of polylogarithms. That page.
oh, I see, I see, I see.
So when, for example, K. Yeah, you missed it.
Oh.
Slowly, I will tell
Uh,
you.
oh yeah, this
This
one.
one. This one.
Yeah.
So, for example, K2, K being 2, dilogarithm.
Mm-hmm.
What was your conjecture? I mean, you have seen some, you have any, how do I put it, hope for a conjecture? Like Baker's theorem, okay, we know it exists, take Fields medal, and yeah, it's a big sledgehammer. What do you expect in the case of K equal to 2, or even N, capital N equal to 2 or 3? Have you even had a look at those numbers?
Yeah, so when k is bigger than 1, the analog of Baker's theorem has been conjectured by Ramurthy, Shaoli Gun, and Purushottam Rath, and they called it the Polylog conjecture.
Great, but if, like, for
That,
example, you might have tried out some values. Like, see, obviously, dilogarithm at 1 is zeta 2. So
yeah,
already there's the pi coming up. And then at any other value, like Zagier has some special values also. Uh,
yes,
but no
yes.
other special values are known. But even then, what is the hope for such a conjecture in the first place? I mean, what is the prognosis
Hope for proving such a conjecture.
for making? I said making. No,
Making.
see, dilogarithm at one is zeta 2.
Uh-huh.
At I, for example, what do you think it should be? Are they even supposed to be linked?
Um, because this is recorded, I am very averse to making any
So
statements
sorry.
like
I
that.
also make any statements. No. I was just saying if you have done anything extra on those conjectures. No, right?
No, so as far as I am aware, understanding the polygamma functions or the polylog functions at, let's say polylog functions at roots of unity
Uh-huh.
is reasonably hard. We do understand values of the polylog, but we understand the values close to zero. Like if you have a 1 over, like instead of the root of unity as the argument, if we have, let's say, 1 over beta, where beta is large enough, then we do understand a little bit of how the values behave. But closer to the unit circle, I
That's
don't.
fine. So you have some. Shall I contact you and you can give me some reference for that part that you just mentioned, 1 by beta?
Okay. Oh yeah, sure,
And that'll be
sure.
great. Thank you very much. That's all.
Oh
I
yeah,
don't have any more questions.
sure. Okay.
So then that would involve Lurch zeta function, right? It would have z being e to the 2 pi I x or something.
So for the Lurch zeta function, we introduce one more wrinkle, that is we have
Yeah.
a shift over here, like n plus alpha to the n. Those would be the Lurch zeta functions, and they would be even trickier because then you don't have even the even at 1 we just have the Hurwitz zeta function, which does not have the multiplicative structure like the Riemann zeta function. So I think that would be even harder. But they are studied. I must say that there are papers, I forget by whom, where they studied, instead of LSF, f of n over n plus alpha to the s. And in that case, you would, instead of getting polylog, you get the Lurch zeta values.
The original Chava Milner conjecture, the word, the terminology was given by Murthy and Shauli and Rothnali. In the
Yeah.
case of Hurwitz zeta function, I thought, right? Wasn't it?
It is. So these poly gamma functions for k bigger than 1 are essentially values of the Hurwitz zeta function.
Hmm.
So that's why we have the Hurwitz zeta function values coming into picture. Yeah.
Okay. Thank you.
So if there are no further questions, may I request everyone to please unmute yourself and clap for Siddhi for a very nice talk.
Thank you.